I'm Debra Fischer, and I'm a professor of astronomy at Yale University. I've been working on exoplanet detection now for over 20 years. My team built a spectrograph which we commissioned in Chile in 2012, the Chiron spectrograph, and the whole purpose of that instrument was to find planets around Alpha Centauri. And for the last decade, my team's really been focused on building an instrument that would deliver the precision we needed to detect Earths around other stars, nearby stars. For me, this is an incredible time because in 2 months we are going to put that instrument together at the Discovery Channel Telescope in Flagstaff, Arizona. And if you're able to come downstairs, I can show you our lab and show you the progress we're making. But what our instrument does is it takes that white light from the star, focuses it from the large telescope onto a fiber that's smaller than a human hair in diameter, and then it disperses the light into a rainbow in the same way that, in a simplistic way that a prism would work. If you hold a prism up to the sun, you'd see a rainbow projected onto your wall. Well, our rainbow actually turns out to be something like 15 feet long. That spectrum gives us an incredible amount of information. It tells us what the star is made out of, and it tells us how fast the star is moving. This is the third instrument that my team has built, and with every iteration we've rolled forward all the things that we think that we need to improve our precision and to get it down to Earth detecting precision. This material that the spectrograph bench is built out of is called INVAR. Everything we've done is to build in redundancy for our stability in this instrument so that we can press down from 1 meter per second precision to 10 centimeters per second precision. That is Earth detecting precision. So that's what we're doing. We'll commission this instrument in a month, 2 months, 6 weeks. 6 weeks at the Discovery Channel Telescope, which is part of Lowell Observatory in Arizona. And we would like to replicate this and put it on the SOAR telescope. SOAR is located in Chile. It is a perfect location for looking at Alpha Centauri A and B and Proxima Centauri. So it's one of the reasons that we'd like to essentially replicate this instrument and put it on SOAR. When I heard about Project Blue, I was incredibly excited that this is an opportunity to actually go up and directly image and see the planets orbiting Alpha Centauri A or Alpha Centauri B. I'd like to couple that observation with an instrument in the southern hemisphere where we could really measure the masses of those planets and begin to characterize them. Alpha Centauri is a star system that has always been intriguing. It's the closest star to the sun. It's the place that when we travel into the galaxy, we will imagine that will be our first stop.